Let's continue on with lesson 4, and we're going to be looking at chemical reactions in a bit more detail, namely single displacement reactions and double displacement reactions. Let's start by reviewing the reaction types that we went over in the last video. So starting with the first reaction type, synthesis, which we called combination, that is where you have two or more reactants that are combining to form one compound, one product. Decomposition, this would be the opposite of a combination. So in the case of decomp, you have just one compound for the reactant, and it is breaking apart into two or more products. Now the next two, single displacement and double displacement, we're going to look at those in a bit more depth in the upcoming slides. So let's define them and review them quickly. So single displacement is where you have an element by itself reacting with a compound. And what happens is that element that's by itself kicks out one of the elements in the compound, in this case the blue one, so that when it comes to the products, the element that was by itself is no longer by itself. It's now in a compound, leaving the element it kicked out by itself. Now, double displacement, in this case, to recognize that, you have two compounds as the reactants. So no elements by themselves, so it's compounds, so they're paired up. And what happens is those two compounds switch partners. And when they switch partners, it's always the outer two, so in this case, the red and the green sphere that form one of the products, and the inner two, the blue and the yellow sphere that form the other product. This is important to note because we're going to look at these reactions and you need to be able to predict what the products are going to be. So it's going to be very useful for you to know that the outer two elements combine and the inner two elements combine. That's the first step in predicting the products. Now, combustion reaction was the other type we saw. So this was a carbon-based compound, a hydrocarbon usually, reacting with oxygen on the reactant side. And the products were always carbon dioxide and water. Now we're going to look at double displacement reactions in a bit more detail because you are going to need to be able to predict the products for these types of reactions and do some other manipulations with them. So for the specific reaction types, we have three for the double displacement. We have precipitation, acid-base neutralization, and gas forming. So we're going to start and look at the precipitation reactions in a bit more detail. So remember, for precipitation reactions, how to identify that it's a precipitation reaction is that it forms a precipitate. So the word precipitate in chemistry just means that it forms a solid. So you can tell this by looking at the reaction scheme because there'll be the letter S after one of the products in parentheses, indicating the solid or precipitate was formed. So if you were predicting the products of a precipitation reaction, how would you tell which one of the products formed a solid? Well, in order to figure that out, you would need to use a solubility table. So you can see the solubility table off to the right on this slide. Now this is the same solubility table that you have glued into your lab manual as one of your reference pages. So we're going to be using this to figure out if a compound is soluble, meaning that it dissolves in the solvent that it's in, or to see if the compound in question is insoluble. Insoluble meaning it precipitates out, it forms a solid. So how do we use the table? For the soluble sections, they are going to be in the upper left-hand corner and the lower right-hand corner. So how do you read this? You can see the title that says soluble ionic compounds. So for the first one here, it is indicating that all sodium, potassium, and ammonium containing compounds will be soluble, and there are no exceptions, because when we follow it over to the notable exception columns, there's no exceptions listed. So that means anytime you see sodium, potassium, or ammonium in an ionic compound, that ionic compound will dissolve will be soluble all the time, no matter what it is attached to. Same thing goes for the second column, because the second column also has no exceptions, right? There's nothing here in the notable exception column. So this is saying that all compounds containing these anions, and I'm calling them anions because they're negatively charged. So if there is nitrate or acetate or chlorate or perchlorate in any ionic compound, no matter what it's attached to, it will be soluble. It will dissolve in the solvent that it's in. Now, the next column does have exceptions. So I'm referring to the chloride, bromide, and iodine salts. So this is saying if chlorine, bromine, or iodine is present, it can be soluble sometimes, and the only time it will not be soluble is when it's with the exceptions. The exceptions being lead, silver, and mercury. So, for instance, if you had a lead chloride compound, that would form a solid. If you had a silver bromide compound, that would form a solid. Or if you had a mercury chlorine compound, that would also form a solid. But if there's any other cations attached to chlorine, bromine, and iodine, they will dissolve. It's only those three metals that are going to form solids with those anions. Next column talks about fluorine. So fluorine can be soluble unless it's with calcium, strontium, barium, and lead. So if it's with any of those four cations, a solid will form. Otherwise, it will dissolve. Next one, sulfate. So the SO4 polyatomic with a 2- charge. That means sulfate ions or containing compounds will dissolve unless they're with the exceptions. So they will only form solids with a sulfate compound if calcium, mercury, strontium, barium, or lead are attached. That's the only time a solid will form with a sulfate. Now I want you to note that when you go to the bottom half of this table, notice it's the opposite. So by opposite, I mean on the left-hand side, they have insoluble compounds, meaning solids on this side. The exceptions are going to mean that they're soluble. That's why we have the soluble sign written on this side. Okay, so it's kind of flipped on the bottom. So this is saying that anything that contains hydroxide or oxide will precipitate out, will form a solid, unless it's with sodium, potassium, or barium. Okay, so if hydroxide is with sodium, for instance, it's going to dissolve. If hydroxide is with potassium, it will dissolve. If it's with barium, it will dissolve. But if hydroxide is with anything else, copper, lead, anything, it's going to form a solid. All right, looking at sulfide, I'll go over this one a little bit quicker. So the sulfide containing compounds will form solids. That's what it's saying. It's going to be insoluble, so it will form solids unless it's with sodium, potassium, ammonium, and barium. So if it's with one of those four cations, it will dissolve and be soluble. Carbonate and phosphate, they usually form solids unless they're with sodium, potassium, or ammonium. Then they will dissolve. So you can see that the soluble sides are going to be in the upper left and the lower right, and the insoluble are going to be in the upper right and the lower left. So that's how you read this table. Now that we know how to read the table, let's do some practice using the table. So we have 5 different examples here of compounds, and the question is asking us to identify the following substance as soluble or not soluble. So remember, soluble means it will dissolve. Not soluble or insoluble means a solid will form, a precipitate will form. So let's add the key so that we know which corners are soluble and insoluble, and let's start with the first one here. So lead 2 chloride. So when I'm trying to figure out if lead 2 chloride is going to form a solid or if it's going to be soluble, I would look for the chloride ion first. So I see chlorine's right here, and it says that chlorine's almost always soluble. The exceptions, so when it's going to form a solid, is if it's attached to lead, silver, or mercury. And in this case, it is attached to lead. So since it's attached to one of the exceptions, this guy is going to be insoluble, meaning it will form a solid. Let's look at the next example. So the next example, we have magnesium iodide. So we're going to go ahead and look for the iodine ion. So iodine is right here in the same area as chlorine. So it's saying iodine is soluble unless it's attached to lead, silver, or mercury. So in this case, is iodine attached to lead, silver, or mercury? No, it's not. It's attached to magnesium, meaning since it's not attached to an exception, it will be soluble. So S for soluble. The next example, we have nickel 2 sulfate. So for nickel 2 sulfate, we want to look for the sulfate ion. So the sulfite ion's down here, so it's saying the sulfite ion is usually soluble unless it's attached to calcium, mercury, strontium, barium, or lead. So in this case, is sulfate attached to one of the exceptions? No, it's not. Nickel is not one of the exceptions, meaning that nickel 2 sulfate will dissolve or be soluble in the solvent that it's in. Copper 2 oxide. So now we're moving to the bottom part of the chart. So here's the oxide ion, O2 minus. Now remember, the bottom half of the chart is opposite. So this is saying that oxide-containing compounds will usually form solids unless they're with sodium, potassium, or barium. So in this case, is oxide with one of the exceptions? No, it's not. Copper is not an exception. So that means that this oxide-containing compound will be insoluble. It will form a solid since it's not with one of the exceptions, because we're on the bottom half, which is opposite of the top. Let's do the last one, calcium fluoride. So finding the fluoride ion, it's in the top half, so it's the soluble section. So it's saying fluorine is usually soluble unless it's with calcium, strontium, barium, or lead. So is fluorine with one of the exceptions in this case? Yes, it is. So if it's with an exception, it is insoluble, forming a solid. Let's now look at an example where we predict the products and then figure out which of the products forms a precipitate or a solid. So given are the two reactants, so the two things we put together in the flask. And when we put these two things together in the flask, we get a bright yellow solid forming. So we know that it's a precipitation reaction due to that bright yellow solid. Now, a lot of times in lab, solids are just going to look like cloudiness. It's not going to form just one perfect chunk of solid. Okay, so whenever you see cloudiness forming when you're mixing two chemicals together, that's indicative of a precipitate or a solid forming. So we know a solid forms, so let's go ahead and predict the products. Well, the first step for predicting them is to know which parts go with which. So we said for double displacement reactions that the outer two compounds, so in this case the ammonium ion and sulfate elements, are going to combine to form one of the products, and then barium and fluorine, the other two elements left, the inner two, are going to form the other product. So we want to write our new products with their charges is the next step. So that means we want to put barium and its charge with fluorine and its charge, and then ammonium and sulfur together with their charges. So when we do that, we get this. So notice for the NH4, the ammonium, it has a +1 charge. For sulfur, it has a -2 charge. Notice the cation, the positively charged ion, always comes first in a chemical compound. The negatively charged anion comes second. So why do we need to include the charges here? Because the charges will tell us what the subscript should be. So we need to know the charges so we can do the crisscross method and figure out what that neutral compound would actually look like in real life. So this is not the final answer. This is just the next step in predicting the products. Moving over to the barium product. So barium, since it's an alkaline earth metal, it has a +2 charge. Fluorine, since it's a halogen, it has a -1 charge. Notice once again, the cation barium comes first in this chemical compound. So what we do next is we do that crisscross method to figure out what the actual products will look like. So that means we take this number 2, not the charge, just the number, and that becomes a subscript on the NH4. So we're going to have 2 ammonium ions and 1 sulfur. For the barium fluoride compound, it looks like we need 1 barium and 2 fluorines. So we get products that look like this. NH4 parentheses around the whole polyatomic with the 2 on the outside, and then 1 sulfur. For the barium fluoride compound, 1 barium and 2 fluorines after the crisscross method. So we have successfully predicted the products. Now we need to figure out which one of the products formed that bright yellow solid. So let's start with the ammonium sulfide compound. So looking at ammonium on this chart, ammonium is the very first row. So we have NH4 plus, and it's saying that ammonium is soluble, meaning it dissolves all the time no matter what it's attached to. So that means that this ammonium compound will not form a solid, so it'll have an AQ by it. Excuse me. That must mean that barium fluoride is going to form the solid, but let's check just to make sure. So going over to the chart, we find fluorine on the chart, and it is right here. So it's saying fluorine compounds are generally soluble unless they're attached to calcium, strontium, barium, or lead. Since barium is one of the exceptions, that means that barium fluoride will form a solid. So we have predicted the products and figured out which of the 2 products forms the solid. Next, we're going to take double displacement reactions for precipitation reactions and learn how to write net ionic equations. So we're going to start with the full molecular equation. So this is a general reaction scheme for double displacement reactions for a precipitation reaction. How do I know it's for a precipitation reaction? Because of this S by one of the products indicating that a solid or a precipitate has formed. So this is the general reaction scheme that you see. So to write the complete ionic equation, what you need to do is anywhere there is an AQ. So for all compounds that have an aqueous written by it, you need to separate those compounds into their counterparts, into their ions. The only one you do not separate into its ions is the one that has an S by it, the solid. So when you do that, it's going to look something like this. So remember that the cation always comes first, so that's why A has the plus sign, and then C has the minus sign. Now, compound DB was also aqueous, so we split that into its ions as well, into D plus and B minus. And then moving over to the product side, we left AB together because it was a solid. So you can only separate them into their ions when they're aqueous. Why? Because if they're aqueous, that means they dissolved in the water that they are in, meaning that when they dissolve, they separate into their ions and you have ions floating around in solution. That is how electricity is conducted with ionic compounds, right? It's the ions, the charges floating around in solution that conducts electricity. So since DC is aqueous, we separated those into D plus and C minus. Now to write the net ionic equation, what you need to do is look at the reactant and product side and see what ions are in common. And those ions that are in common are actually highlighted. So you can see the C minus compound on the reactant side is also present on the product side in exactly the same form. So that's why it's highlighted. D plus, same thing. It's present on both sides of that arrow in the same exact form. So since it's present on both sides of the arrow, that means they cancel each other out. So you can cancel out the C and you can cancel out the D. Now for the net ionic equation, you include whatever ions or solids are left. So in this case, it's going to be A plus B minus gives you the solid AB. Now those ions that we canceled out that were the same on both sides that were highlighted, we refer to those as spectator ions because they are not needed to form the solid. So we can cancel them out as long as they're the same on both sides of the arrow. Let's look at another example with actual compounds instead of the arbitrary A, B, and C, D. So here we have copper 2 nitrate reacting with sodium hydroxide to form copper 2 hydroxide and sodium nitrate. So all the compounds that have an AQ by them, those can be separated into their ions. So the only one we wouldn't separate out would be this copper 2 hydroxide solution. So looking at this, which two would be the spectator ions? So remember, it's going to be the ions that are the same on both sides of the equation. So looking at this, it looks like sodium is on both sides. And it also looks like the nitrate is going to be aqueous on both sides. So that means that the sodium and the NO3 are the spectator ions. So those are the ones that are going to cancel out. That also means then that the copper and the hydroxide ion on the reactant side, those are the two ions that form the solid on the product side. So those are the precipitation forming ions. So when we write our net ionic equation, we only want to include the ions that form the solid. So our net ionic equation would be copper 2 plus mixed with 2 hydroxide ions to get the solid copper 2 hydroxide. So this was kind of a shortcut way. We didn't write out all the ions and do the canceling. Next, we're going to stay with double displacement reactions, but we're going to look at the acid-base neutralization reactions, so the second type. So you do need to be able to predict products for these ones as well. Remember for acid-base neutralization reactions that one of the products is always going to be water. And we're also going to learn how to do net ionic equations for the acid-base neutralization reaction. So it's going to be very similar to what we saw for precipitation reactions. Before we look at specific acid-base neutralization reactions, let's define the acids that we are going to be looking at. So we've already learned how to name the acids that we're going to be exploring in this course, but the types of acids that we're exploring are called Arrhenius acids. Now remember, acids, when they are dissolved in water, completely dissociate into their counterparts, their ions. So H plus and the A- ions, making acids ionic compounds when dissolved in water. So there are strong acids and weak acids. So strong acids completely ionize, weak acids only partially ionize to form that H+ ion. Now off to the right you can see a pH scale. So the numbers along the bottom are indicating the pHs. So we start at 1 and go all the way up to 7. So it stops there because 7 here is neutral. So if you are below a pH of 7, that means that it is acidic. Above a pH of 7 would then be basic. So the lower the number, the more acidic it is. So we have pH of 1 being the most acidic. Examples of some substances that are very acidic would be hydrochloric acid. As you move up the pH scale, you get less acidic. So around a pH of 3, we have colas. So colas are slightly acidic. Moving up to a pH of 4, we get into the wine region. So wine's also being acidic. And then as we get closer to the basic compounds, you can see we have things such as mineral water. Now for the bases. So remember the bases that we're exploring in this course are going to be hydroxide bases. So they're going to have that OH polyatomic in them. So just like with the acids, when bases are dissolved in water, they separate into their counterparts and are ionic compounds. So looking at strong bases versus weak bases, it's going to be very similar to acids. Strong bases completely ionize to provide that hydroxide polyatomic. Weak bases are going to only partially ionize to provide the OH-. So looking at the pH scale, this is the other half of it. So we're looking at all of the pH values above neutral, so above the 7. So when we get to a pH of 8, we're slightly basic. So looking at soap, soap is going to be a slightly basic compound. Then we get into laundry detergent around a pH of 10. And the strongest base, referred to as lye for its common name, is actually sodium hydroxide. And we'll be using that in lab a few times with a pH around 14. So the scale of pH goes all the way from 1 to 14. Anything above 7 is basic, anything below 7 is acidic, 7 being neutral. So you can see the purpose of a neutralization reaction is to take a strong acid and a strong base and come up with a neutral product. Hence why one of the products is water. So water being neutral right around that pH of 7. The other product in a neutralization reaction is then going to be a salt. An example of a neutralization reaction is below. So in this case, we have strontium hydroxide base reacting with sulfuric acid to produce a salt and water. Now notice it is a double displacement reaction, so it does follow the same scheme where the outer two elements combine to form one of the products. So in this case, strontium and the sulfate ion combine to form strontium sulfate. And then what's left over, the inner two compounds, hydrogen and OH, form the other product, HOH, making H2O, which is water. So you need to know how to write net ionic equations for neutralization reactions as well. And it's exactly the same way that we did for precipitation reactions. So here's a general reaction scheme. So the first compound being the acid, because it has the H in front. The second reactant compound being the base, because it has the OH. Notice one of the products is water. So remember, when we are doing net ionic equations, any compound that's aqueous, we separate into its counterparts. meaning it's ions. And then in this case, instead of the compound that's the solid, we're looking at the compound that has an L by it. So the compound that has an L by it, the liquid, this is not going to ionize. Okay, so it's going to stay together. We're not going to separate that out into its ions. So to write the complete ionic equation for this, we would have H plus, C minus, D plus, OH minus on the reactant side. And then on the product side, we keep water together since it's a liquid, and the DC will separate into its counterpart since it was aqueous. Notice the spectator ions are highlighted. Spectator ions being the ions that are the same on both sides of that arrow. And since they're the same on both sides, we cancel them out and they do not become part of the net ionic equation. What becomes part of the net ionic equation is what's left. And what's left should be just the two ions that form our liquid, which is water. So net ionic equation is H plus OH minus gives us water. So as you can see, since water is always one of the products for neutralization reactions, this will be the net ionic equation every time for a neutralization reaction in this course. Let's do a practice problem. So what would be the net ionic equation for the neutralization reaction of barium hydroxide and hydroiodic acid? Well, as you saw from the previous slide, you could probably figure that out without going through all of the steps, but I'm going to go through them anyway, just so that you can see. So they gave you the names, so you would need to take the names and turn them into formulas by writing the charges of each element and doing the crisscross method to figure out what the actual reactant should look like. So we have BaOH2 reacting with HI. So our next steps will be to write the balanced chemical equation with the products. Then we will determine the spectator ions and get rid of those so that we can figure out what the net ionic equation should be. So here is the balanced chemical equation. Next, we need to determine the spectator ions. So anything with an AQ by it can be separated into its ions. So the only thing that is not going to change at all is going to be this H2O because it has a L by it, indicating it's the liquid. So anything that is not forming water is going to be a spectator ion, meaning that barium and iodine are the spectator ions. So those are going to cancel out on both sides of the equation. The water-forming ions are going to be hydrogen and the OH. So those are the two that are going to remain in the net ionic equation. So our net ionic equation, once we balance it, becomes 2 H pluses plus 2 OH minuses to form 2 waters. Now notice, since there is a 2 coefficient in front of every single reactant and every single product, that can be simplified down where there's a 1 for a coefficient in front of each. So it would just be H plus aqueous plus OH minus aqueous to form liquid water. The last type of double displacement reaction that we are going to look at is the gas-forming reactions. Since we already went over the other two in quite a bit of detail, we'll go over through this one quickly. So notice it is double displacement once again, and to identify it as gas-forming, you would look for a product that has a G by it. So for gas-forming reactions, there's two different types of reaction schemes. So what's the difference between these? Well, in the first reaction scheme, you can see that the two reactants are aqueous, meaning that they are dissolved in water. One of the products does form a gas, indicating that it is indeed a gas-forming reaction. Now, in the second type of reaction scheme, the difference here is that one of the reactants is a solid. So the example I like to use here is when you think of doing baking soda and vinegar. You know how you make like volcanoes? So baking soda would be the solid. Vinegar would be the aqueous, other reactant. And what you get out is an aqueous product and a gas, carbon dioxide in the case of that example I just gave. So looking at an example below, we have the first type of reaction scheme it looks like, since both of the reactants are aqueous, meaning dissolved in water. So we have ammonium chloride and potassium hydroxide reacting to form liquid water, but also a gas, so that's why it's a gas-forming reaction, and then a salt, potassium chloride. Now you're not going to be asked to do ionic equations for gas-forming reactions. It'll just be for the neutralization and the precipitation reactions. So we're not going to explore that at this time.